Welcome back to statistics. Today, we're going to be talking about ANOVA and post hoc tests. But before we begin, let's review the main points from the last lecture. In the last lecture, we talked about t-tests and error. There are two kinds of error we can make when we use a t-test to decide whether two means are significantly different. The first kind of error is called type 1 error. This kind of error occurs when, in fact, the population means that we're comparing are the same, but the t-test indicates that the difference between the means is statistically significant. Now, whenever we use a t-test, there's a risk we'll make this kind of error. The probability that we'll make this kind of error is represented by the Greek letter alpha. Alpha is also the area of the critical region when we do a t-test. The researchers choose how large or how small alpha will be. Now, usually researchers choose to set the level of alpha at 0.05. That is, they set alpha so that the risk of a type 1 error is 0.05 or 5%. If a researcher wants to, she can choose to set alpha lower at 0.01. Setting alpha at 0.01 reduces the risk of type 1 error to only 0.01 or 1%, but it increases the risk of another kind of error, which is called type 2 error. Now, type 2 error occurs when, in fact, the population means are different, but the t-test indicates that the difference between the means is not statistically significant. The probability that we'll make this kind of error is represented by the Greek letter beta. Beta is also equal to the area of the true sampling distribution that is less than the critical value for t. An important point is that type 1 and type 2 error are unavoidable when we do a t-test. These kinds of error are just a part of using the t-test. They're not due to a mistake or carelessness by the researcher. Now, in the last lecture, we also learned about statistical power. Statistical power is equal to 1 minus beta, where beta is the probability of committing a type 2 error. So, power is equal to the probability of avoiding a type 2 error. Put another way, power is the probability of finding a statistically significant difference between sample means if the population means really are different. Now, in the last lecture, we learned a sad truth. Reducing type 1 error increases type 2 error. Put another way, if we reduce alpha, then that always increases beta. Fortunately, there's a way to keep both alpha and beta small and to increase statistical power. The way to do this is by increasing our sample size, which is n, the number of individuals in our study. Increasing the sample size keeps alpha low, which is a good thing. It decreases beta, which is also a good thing. And it decreases and it increases power. So that's another good thing. Now, I hope I said that right. Keeps alpha low, decreases beta, and increases power. In the last lecture, we also learned the technical definition of type 1 error, which is rejecting the null hypothesis when in fact it is true. We also learned the technical definition of type 2 error. Accepting the null hypothesis when in fact it is false. There are two memory tricks, two mnemonics that can help you remember the definitions. First of all, it's all about the null hypothesis. So here's a cartoon of the null hypothesis saying, it's all about me. The second mnemonic is that type 1 error involves rejecting the null hypothesis. So here's a cartoon of the null hypothesis crying, I'm number 1 and you're rejecting me. Now, these cartoons are obviously ridiculous, but research has shown that mnemonics are more easily remembered if they're ridiculous, violent, or obscene. So for this course, we're sticking with ridiculous. All right, so that's it for the last lecture. Now we're ready to cover some new topics for today. Our big topic today is ANOVA. ANOVA is a statistical procedure that's used to compare groups and see if the groups have different means. The name of ANOVA is an acronym, an abbreviation. The letters ANOVA stand for Analysis of Variance. I won't go into a long explanation of the name here today, but I will point out that you already know what variance is. Variance is also known as the mean square. It's the mean of the squared deviations. So ANOVA involves analyzing the squared deviations. Now, we're not going to go into the technical details here today, but you'll learn all the details about ANOVA if you take the psychology department's course in advanced statistics. ANOVA is very closely related to our old friend, the t-test, though there are some differences. Let's talk about the most important way that ANOVA and the t-test are alike, and the most important ways they're different. As you know, the t-test is used to compare the mean of two groups to see if the means are different. Let's briefly review how the t-test works. We'll use bar graph. It's based on a real study that looked at how the COVID-19 lockdown affected depression in a group of pregnant women. The height of the bars shows the scores of these pregnant women on a questionnaire measuring depression. The bar on the left shows the average depression scores of a group of pregnant women during the 6-week period just before their city went into lockdown. As you can see, these women had average depression scores that were slightly less than 5. So on average, maybe this group was slightly depressed. That's not a real high score, but it indicates the presence of some depressive symptoms. The bar on the right shows the average depression scores of another group of pregnant women during the 6-week period immediately after their city went into lockdown. As you can see, these women had average depression scores that were slightly more than 5. So this is a comparison of depression scores right before the lockdown and right after the lockdown. Now, as we've seen earlier in this course, we can compare the depression score in the two groups of women by doing a t-test. And if we do that, we find that t equals 0.737 and p equals 0.461. the probability value, P, is 0.461, which is greater than 0.05. So this tells us that the difference between the two groups is not statistically significant, and we should accept the null hypothesis. Now, here's the null hypothesis for a t-test. Mu1 is equal to mu2. That is, if the null hypothesis is true, the population means are the same. Okay, so that's it. According to the null hypothesis, the population means are the same. Now, in this example, because P is greater than 0.05, we accept the null hypothesis. That is, we accept the hypothesis that the means of the two groups are the same. Put another way, we conclude that women's depression levels did not change before and right after the lockdown. Now that we've reviewed the t-test, let's look at ANOVA and see how it's similar to the t-test, but a little different. ANOVA is used when we want to compare the means of two or more groups. So we can use ANOVA to compare the means of two groups if we want, but we can also use ANOVA to compare three groups, four groups, or more. We can't do that with a t-test because a t-test is only good if we're comparing two groups. Now, this bar graph is just like the one we were looking at a moment ago, but it shows three groups instead of two. Again, each bar represents the depression scores of a group of pregnant women. The first bar on the left shows the average depression score for women during the time period 1 to 6 weeks before the COVID-19 shutdown in March 2020. The bar in the middle shows average depression scores of women during the time period 1 to 6 weeks after the shutdown. So these two bars on the left are the same ones we saw a moment ago when we were reviewing the t-test. But the bar on the right is new. It shows the depression scores of women during the time period 7 to 12 weeks after the shutdown. In other words, it shows the scores for women during May and early June after the shutdown. As you can see, the average depression score in this group of women is a little less than 4. Now, to compare the means of these three groups, we cannot use the t-test because the t-test is only for comparing two groups. Instead, to compare these three groups, we have to do an ANOVA. So we do that, and the ANOVA produces a statistic called F. When we do a t-test, we do our calculations and get T. When we do an ANOVA, we do our calculations and get F. Now, for the groups in this graph, F is equal to 3.56 and P is equal to 0.029. We interpret these numbers in a very similar way to the way we interpret the numbers in a t-test. The probability value P is equal to 0.09, which is less than 0.05. So that tells us that F is statistically significant. Whenever F is statistically significant, we reject the null hypothesis. The null hypothesis in this case is that the population means for all three groups are the same. That is, mu1 equals mu2 equals mu3. Because P is less than 0.05, we should reject this null hypothesis. The means are not all the same. Instead, we conclude that two or more of the means differ from each other. So let's sum up what we've just learned in this example. ANOVA is used to compare two or more means. For ANOVA, we calculate the statistic F. If F is statistically significant with P less than 0.05, we reject the null hypothesis, and we conclude that two or more of the population means are different from each other. Okay, now that we have an overview of ANOVA, let's focus on some very important details. The first detail is that we can use either ANOVA or a t-test to compare two groups. If we have only two groups, either ANOVA or the t-test will work. So here's the bar graph with only two bars that we saw when we were reviewing the t-test. The left bar represents depression in pregnant women 1 to 6 weeks before the COVID-19 shutdown. The right bar represents women 1 to 6 weeks after the shutdown. As we saw earlier, we can do a t-test to compare the means, and we find that t is equal to 0.737 and p equals 0.461. But here's the new point. If we like, instead of doing a t-test, we can do an ANOVA and calculate F. If we do that, we find that F equals 0.544 and P equals 0.461. And notice something interesting. The probability value P when we do a t-test is 0.461, and that's exactly the same probability value that we get when we use F. So the results of the t-test and the results of the ANOVA are in total agreement. They both tell us that P equals 0.461, and we should accept the null hypothesis. So this turns out to be a general rule. When we want to compare the means of two groups, we can use either a t-test or ANOVA, and it really doesn't matter which we use, because the p-value will be the same either way, and we will reach the same conclusion either way. If you read scientific journals, you'll see that when researchers are comparing two groups, some researchers use the t-test and others use ANOVA. Both approaches are considered okay for this purpose, both t-test and ANOVA. So to sum up this first detail, we can use either ANOVA or a t-test to compare two groups. And whichever we use, P will be the same, and we will reach the same conclusion. Now let's go on to the second detail about ANOVA. This is about something called degrees of freedom. Now, here's one of the bar graphs we've been using as an example. It's the one with three groups of women. And at the top, we see what we saw before, that F is equal to 3.56 and P is equal to 0.029. But maybe you notice these two numbers that are written in parentheses next to F, 2 and 477. These two numbers are called the degrees of freedom. Or for short, they're sometimes called just DF. Whenever we write F, the F statistic at the top, we write the degrees for freedom beside it. The degrees of freedom provide information about the number of groups being compared and the total number of people in these groups. The first degree of freedom, which is written on the left side, is equal to the number of groups being compared minus 1. Now, in this example, 3 groups are being compared. Each group is represented by a bar in the graph. These 3 groups, so there's 3 groups, 3 minus 1 equals 2. So the first degree of freedom is 2. The second degree of freedom, which is written on the right side, is almost equal to n. N is the total number of individuals in the study. Now, in this study, there were 160 women, pregnant women, in the first group, 160 in the second group, and 160 in the third group. So, the total number of women in the study, that is n, was 160 plus 160 plus 160, which is equal to 480. So n equals 480. Now, here's the important point. The second degree of freedom is 477. Which is almost 480. So that's what we mean when we say that the second degree of freedom is almost n. In this example, the second degree of freedom, which is 477, is almost equal to n, which is 480. Now, as you'll learn later on if you take advanced statistics, there's actually a complicated formula for calculating the second degree of freedom, which we're not going to explain here today. For right now, all you need to remember is that the second degree of freedom is almost n. It's always just a little bit less than n. That's a little, not exact, but it really gives you the general idea. It's almost there. Now, here's the other example we've been using today. And at the top are T, F, and the probability values. So let's get rid of T because we don't need it right now. And we'll move F up a bit. Now let's look more closely at the degrees of freedom. The first degree of freedom on the left is supposed to be equal to the number of groups minus 1. Well, the number of groups in this example is 2. Oh, just a second. I need to go back 1. The number of groups in this example is 2. There are 2 bars. So 2 minus 1 is equal to 1. So yes, you can see the first degree of freedom is 1, just like it's supposed to be. Second degree of freedom is supposed to be almost n. Well, let's calculate n. The number of pregnant women in the first group is 160. The number of women in the second group is also 160. So n, the total number of women in the study, is 160 plus 160, which is equal to 320. Now, the second degree of freedom is 318, which is just a little less than 320. So yes, this fits with what we saw earlier. The second degree of freedom is a little less than n. So let's sum up what we just learned about degrees of freedom. The degrees of freedom are always written in parentheses right next to f. The first degree of freedom is equal to the number of groups being compared minus 1. So we can actually use the first degree of freedom to figure out how many groups are being compared. We just add 1 to the first degree of freedom, and that tells us the number of groups. The second degree of freedom is almost equal to n. So we can use the second degree of freedom to estimate the total number of individuals in the study. We may not be sure of the exact n, but we can come very close. Next, let's talk about the third detail about ANOVA. How do we tell if F is statistically significant? Now, with the t-test, it's fairly easy to tell. If t is greater than the critical value of 2, then it's statistically significant. How easy? But F is more complicated than that. It is true that F, like T, is statistically significant if it is larger than the critical value. But the critical value of F changes depending on the degrees of freedom. So it keeps changing depending on how many degrees of freedom you have. It's not always 2 or some number. Now, for kind of a rough estimate, you should probably remember that if F is greater than 4, it's almost always significant, right? So usually if F is greater than 4, you can be pretty sure it's statistically significant. If F is less than 2, you can also be pretty sure it's not significant, because F less than 2 is almost never significant, except very rarely. But if F is between 2 and 4, maybe it's significant, and maybe it's not. So looking at F and trying to figure out whether it's significant is kind of a mess. So if F is so complicated, how do you tell if it is statistically significant? My advice is, don't worry all that much about F. Instead, just look at P. If P is less than 0.05, then you automatically know that F is greater than the critical value, whatever it is, and it's statistically significant. If P is greater than or equal to 0.05, you automatically know that F is less than the critical value and is not statistically significant. So, for instance, in this example, P is equal to 0.029. P is less than 0.05, so we automatically know that F must be statistically significant. Or as another example, here we see that P equals 0.461. P is greater than 0.05, so we automatically know that F is not statistically significant. Okay. So now let's move on to another detail about ANOVA. So let's say we've looked at P and we found that F is significant. When F is significant, what can we conclude? As a comparison, let's remember what we already know about the t-test. When T is significant, we reject the null hypothesis. For the t-test, the null hypothesis is that the population mean of the two groups, the population means of the two groups are equal to each other. That is, mu1 equals mu2. So if T is significant, we reject the null hypothesis, and we conclude that the population means of the two groups are not the same. Now let's compare that with what we do when F is significant. It's a lot like what we do what we do when F is significant is a lot like what we do when T is significant. When we perform an ANOVA and F is significant, we reject the null hypothesis. Now for ANOVA, the null hypothesis is that the population means of all the groups are equal to each other. For instance, if there are 3 groups, the null hypothesis is that mu1 equals mu2 equals mu3. If we reject that null hypothesis, we conclude that the population means are not all the same. Or to put it another way, we conclude that the population means of 2 or more groups are different from each other. Or we can say, I've written here, population means of at least 2 groups are different from each other. So let's summarize. When F is significant, what can we conclude? We can conclude that the population means of at least 2 of the groups are different from each other. But that doesn't mean that all of the population means are different from each other. Some of the population means may be the same. Maybe. So here's our example again. We can see that F is statistically significant because P is equal to 0.029. So what can we conclude now that we know that F is statistically significant? We can conclude that the means are not all the same. At least 2 of the means are different from each other. But there's still a big question. Exactly which means are different from each other? It looks like the bar in the middle is a lot higher than the bar on the far right. So these 2 groups probably have means different from each other. But how about that bar on the far left? Do you think it's different from the middle bar and from the bar on the far right? It's kind of hard to be sure. And when we're using statistics, right, we want a better answer than I kind of think so. So that's why we have something called post hoc tests. And that's the second main topic of today's lecture. Post hoc tests go along with ANOVA. And they're what we'll be talking about during most of the rest of today's lecture. Here's why we need post hoc tests. When we do an ANOVA and F is statistically significant, we conclude that the means aren't all the same. But we still don't know exactly which of the means are different from each other. And that's why we need post hoc tests, because post hoc tests tell us exactly which means are different from each other. The words post hoc are Latin. They mean after. So post hoc tests are done after we have done an ANOVA and after we found that F is statistically significant. And the purpose is to find out which means are different from each other. So as an example, let's use the findings from the study of depression in pregnant women before and after the COVID-19 lockdown. We already know that F is statistically significant. So we know at least 2 of the means are different from each other. So now we're going to use post hoc tests to see which means exactly are different from each other. Now, the group of women on the left were measured 1 to 6 weeks before the lockdown and their mean depression score was 4.8. That's the exact number. The women in the middle were measured 1 to 6 weeks after the lockdown, and their mean depression score was 5.2. Now here's a question for you to think about. Do you think the depression scores for this group were significantly higher than the scores for the group on the left, which was measured before the shutdown? In other words, do you think that depression significantly increased after the lockdown began? Okay, by the time we get to the end, you'll know the answer to that question, but make a guess now. You don't have to tell anybody. Now, finally, the women on the right were measured 7 to 12 weeks after the lockdown, and their mean depression score was 3.9. So here's another question to think about. Do you think that the depression scores in this group on the far right were significantly lower than the scores in the other two groups? Just something to think about. We'll find the answers. So now we're going to find those answers we're going to find the answers of these questions using post hoc tests. Now, this is a computer program, or not a computer program, computer printout that shows the post hoc test. Boy, I'm having trouble with that today. It shows the post hoc tests for the three groups of pregnant women in the depression study. And you should know, there are several different kinds of post hoc tests that computers will do. We'll be using one of these tests that's called the Scheffé post hoc test, which is very widely used for post hoc tests. And the Scheffé post hoc test was developed by a famous American statistician named Henry, you guessed it, Scheffé. The top of the printout has headings, and below the headings there are 3 rows. Each of these 3 rows reports the result on a post hoc test. And we'll look at these 3 rows one by one. We'll begin by looking at the first row. Over here on the left, in the yellow box, we can see the 2 groups that are being compared. On the left, it says 1 to 6 weeks before, and on the right, it says 1 to 6 weeks after. So in this row, the 2 groups being compared are the pregnant women who were measured 1 to 6 weeks before the COVID lockdown, and the pregnant women who were measured 1 to 6 weeks after the COVID lockdown. So these are the 2 groups that are being compared. The bar on the left represents women who were measured 1 to 6 weeks before the lockdown, and their mean depression score was 4.8. The bar on the right represents women who were measured 1 to 6 weeks after the lockdown. Their mean depression score was 5.2. So these are the 2 groups being compared in this first row of the printout. Here, the print in the yellow box, the new yellow box, the printout reports the difference between the means of the 2 groups. Now, as we've just seen, the means of the 2 groups are 4.8 and 5.2. The difference between these 2 means is 4.8 minus 5.2, which is equal to negative 0.4. So the difference between the means is negative 0.4 or negative 0.4. Now, is that difference big enough to be statistically significant? To find out that, we look over here. This is P, or the probability value for the difference. P is equal to 0.743. P is larger than 0.05, quite a bit larger. So this tells us that the difference between these 2 groups is not statistically significant. So the means of these 2 groups are not significantly different. This tells us that the women's depression levels did not go up significantly between the 6 weeks before the shutdown and the 6 weeks after the shutdown. There was not a significant change. Okay, so now we've finished with row 1. Let's go on to row 2. The two groups that are being compared in this row are, first, the women who were measured 1 to 6 weeks before the lockdown, and second, the women who were measured 7 to 12 weeks after the lockdown. So these are the two groups being compared now. The bar on the far left represents women who were measured 1 to 6 weeks before the lockdown, and their mean depression score was 4.8. The bar on the far right represents women who were measured 7 to 12 weeks after the lockdown, and their mean depression score was 3.9. We compare the means of these two groups by calculating the difference between the means. 4.8 minus 3.9 equals 0.9. So the difference between the means is 0.9. So let's see. Is a difference of 0.9 between the means large enough to be statistically significant? And here's the answer. The probability value, p, is equal to 0.190. 0.190 is greater than 0.05. So the difference between these two means, which is 0.9, is not statistically significant. So the means of these two groups are not significantly different. Okay, so now we're finished with this row of the printout, and now we'll look at the third row. This row is comparing the women measured 1 to 6 weeks after the lockdown with the women measured 7 to 12 weeks after the lockdown. In other words, these two groups are being compared. Their mean depression scores were 5.2 and 3.9. So, for these groups, we calculate the difference between the means. 5.2 minus 3.9 equals 1.3. So the difference between these two means is 1.3. So what do you think? Is that difference big enough to be statistically significant? The answer is yes. P is equal to 0.035. 0.035 is less than 0.05. So the difference between these two means is statistically significant. Good news. These are the two groups, and we now know that the means of these two groups are significantly different. So now we have finished comparing all the means. And here are the results. We compared all the means with each other using post-hoc tests, and we found that only two of these means are significantly different from each other. These two. So what do we conclude now that we've finished the post-hoc tests? We can conclude that among the pregnant women, depression was significantly lower 7 to 12 weeks after the shutdown than it was 1 to 6 weeks after the shutdown. In other words, depression actually went down between these two time periods. And by the way, this was a real study, and the researchers did not expect these results. They expected that women would become more depressed during the shutdown, not less depressed. But that's the way it goes with research. Things don't always turn out the way that we expect. The real world isn't necessarily the same as the picture we have of it in our heads, even if we're scientists. Okay, so at this point, you have learned about ANOVA and post hoc tests. So now I'm going to give you one more extended example of how ANOVA and post hoc tests are used or can be used in a study. And the example I'm going to give you is based on a real experiment that was actually conducted at UTEP. In this study, students were witnesses, or they saw what they thought was a real theft. It was staged in the lab, but they didn't know it was fake when it went on. After this staged or this fake theft, they were questioned about what they had seen during the theft, as if they were real witnesses to a crime. And there were three kinds of questioning used. One group of students was given false information when they were questioned. For instance, students in this group were told falsely that according to other witnesses, the thief was wearing a green shirt. In fact, the thief had worn a blue shirt. After being given this false information about the green shirt, the students were asked what color shirt did they remember the thief was wearing. So they answered the question, but they answered after they were given false information about what the other witnesses had said. A second group of students was given true information when they were questioned. For instance, students in this group were told that, according to other witnesses, the thief was wearing a blue shirt. Now, of course, this information was actually true. The thief really had worn a blue shirt. So after being given this true information, the students were asked what color shirt they remembered the thief was wearing. A third group of students was given no information when they were questioned. That is, they weren't told anything about what other witnesses had said. For instance, the students in this group were simply asked what color shirt they remembered the thief was wearing, with no other information. So those were the three groups. Witnesses that were given false information, those that were given true information, those that were given no information. And they were asked, I think, about 5 or 6 questions about the theft. And they could, the study then studied the number of correct answers they gave to these questions. And the research question of the study was, will the students' accuracy during questioning be affected by the true or false information that they were given? So will this true or false information affect the number correct or incorrect answers that the students gave when they were questioned? Now here's the results. The height of the 3 bars show how many correct answers the students in each group gave when they were questioned about the theft. The bar on the left shows the mean number of correct answers given by students who were given true information before they answered a question. And as you can see, students in this group gave the highest number of correct answers, a little more than 3. Those questions were not easy. There were 5 or 6 questions, and the average was about 3 correct. The bar on the right shows the mean number of correct answers given by students who were given false information before they answered questions. Now, as you can see, students in this group gave the lowest number of correct answers, a little less than 2 on average. The bar in the middle shows the mean number of correct answers given by students who were not given any information at all before they answered the questions. And as you can see, the number of correct answers for this group fell between the other 2 groups, with an average of more than 2. Now, I'm going to do an ANOVA to analyze the results of this study. But before I calculate F, I'd like to ask you some questions about the degrees of freedom for F. Here's the first question. As you can see, there are 3 groups in this study. So what number should we write up in the top left as the first degree of freedom? I'm going to give you just a minute to think of the answer. Okay, here's the answer. The first degree of freedom is equal to the number of groups minus 1. There are 3 groups in this study. 3 minus 1 is 2. So the first degree of freedom is 2. So now let's turn our attention to the second degree of freedom. There were 3 groups in this study, and there were 30 students in each group. So here's another question for you. What number should we write for the second degree of freedom for F? You may not know the exact number, but you can make a really good estimate. So let me repeat the question. What number should we write for the second degree of freedom? Okay, I'll give you a moment to think about it. Okay, here's the answer. The second degree of freedom is almost equal to n, the total number of individuals in the study. In this study, there are 3 groups and each contains 30 individuals. So n equals 30 plus 30 plus 30, which is equal to 90. So the second degree of freedom must be almost 90. It could be 86, it could be 87, or it could be 88. Who knows? But in fact, the second degree of freedom is 0.87. But give yourself credit. If you said 86, 87, 88, or 89, those are all excellent estimates, and it shows that you understand how this works. Okay, now that we know the degrees of freedom, let's go on with the ANOVA. In this study, F equals 10.69 and P is equal to 0.002. Now, here's a question for you. Is F statistically significant? Okay, have you decided? Good. Now, here's the answer. F is definitely statistically significant. And there are 2 ways we can tell that. First, F is 10.69. As we learned earlier, F is almost always statistically significant if it's greater than 4. Second, we know that F is significant because P is 0.002, which is less than 0.05. And as we learned earlier, the easiest and surest way to decide if F is significant is to just look at P. Now that we know that F is significant, we can draw several conclusions. First, we can reject the null hypothesis. Second, we can conclude that the population means of the 3 groups are not all the same. And third, we can conclude that 2 or more of the means are different from each other. These 3 conclusions are really just 3 ways of expressing the same idea. But now that we know that the means are not all the same, we still face an important question. Exactly which means are different from each other? The ANOVA didn't tell us that. To answer that question, we have to go to post hoc tests. So let's do that. Here are our 3 groups. And here are their exact means. 3.18, 2.34, and 1.82. Which of these three means are different from each other? This printout of the post-hoc tests will tell us. Let's begin by looking at the first row. This row is comparing the students who were given true information when answering questions and students who were given no information when answering questions. So these are the two groups being compared. The mean number of correct answers was 3.18 for students given true information and 2.34 for students given no information. So let's look at the difference between the means. 3.18 minus 2.34 equals 0.84. So the difference between these two means is 0.84. Now, is that difference of 0.84 statistically significant? The answer is yes. The probability value, P, is 0.021, which is less than 0.05. So the difference, which is 0.84, is statistically significant. So the means of these two groups are significantly different from each other. That is, the students given true information gave more correct answers than the students given no information. So now we're finished with this row and can go on to the next one. This row compares the students given true information with the students given false information. So we're comparing these two groups. The mean for the students given true information is 3.18, and the mean for the students given false information is 1.82. So let's look at the difference between the two means. 3.18 minus 1.82 equals 1.36. So here's a question. Is the difference between the two, if the difference between the two means is 1.36, is this difference large enough to be statistically significant? Again, the answer is yes. The probability value, P, is 0.001, which is less than 0.05. So the difference is statistically significant. So the means of these two groups are significantly different from each other. That is, the students given true information gave more correct answers than the students given false information. Okay, so now we're ready to look at the third row. This row compares the students given false information with the students given no information. Excuse me, here they are, the two groups, false information, no information. So these are the groups being compared with means of 2.34 and 1.82. Let's look at the difference between these means. 1.82 minus 2.34 equals negative 0.52. So the difference between the means is negative 0.52. But here's the question, is it a statistically significant difference? The answer is no. The probability value, P, is 0.229, which is greater than 0.05. So since it's greater than 0.05, the difference between the two means is not statistically significant. In other words, the means of these two groups are not significantly different. So that means that the students given false information did not give significantly fewer correct answers than the students given no information. Okay, now we have finished looking at the printout and the post-hoc tests. We did 3 comparisons, and here's what we found. Some of the differences among means are significant, but some are not significant. These are the ones that turned out to be significantly different. So what's our conclusion? Our conclusion is that students given true information were significantly more accurate than students given false information and students given no information. Okay, so that concludes our example of how to interpret the results of an ANOVA with post-hoc tests. And before we finish today, I want to say congratulations. You have now arrived at the end of the last lecture for this course. Now that's an important milestone, and you can feel proud of reaching it. But just a reminder that the course isn't quite over yet. We still have the final exam ahead, and before that, we have the review packet for the final and a review session to go over the problems in the review packet. So this is not adios, not yet. It's hasta luego. We'll be seeing each other again before long.